here. All right, so this is worksheet number 5. I'm starting the recording a bit late, my apologies. So we were just saying that of the two electrodes, the lead electrode had the greater reduction potential compared to cobalt. So lead is the cathode, and it's going to be a reduction half reaction. But I was saying that there's more than one cobalt reaction on the chart. Make sure you're looking for the right one. We want cobalt, or just CO. And if you look at the beaker, it says cobalt nitrate, and there's 2 nitrates attached to that cobalt. That means the cobalt there is 2 positive. So we're looking for a half reaction with cobalt and cobalt 2 positive. That's what the half reaction has to have. So I chose the correct reaction there, and the the oxidation potential is positive 0.28 volts. Combining those together, you get a standard potential, pretty small, but positive 0.15 volts. Does everybody understand that when your standard potential is positive, the reaction is spontaneous? Okay, so a positive cell potential means a spontaneous reaction. What does that mean to say it's spontaneous? It means if you calculate Kc, it's going to be bigger than 1. It's product favored. It also means if you put a piece of cobalt metal, looking at my balanced equation, if you put a piece of cobalt metal into a solution of lead 2+, you would expect to see a reaction happen because the products are favored. But the reverse reaction is non-spontaneous. So if you put a piece of lead metal into a cobalt solution, you would not expect to see a reaction happen there. In the overall reaction, it's all 1-to-1 ratios. So Q is just the cobalt divided by the lead concentrations. Putting the numbers from the picture, we get that the value for Q is again less than 1. And so when Q is less than 1, the natural log of Q will be a negative number, which means E cell will increase compared to E naught, right? Because the natural log of Q is a negative number. The Nernst equation, you end up getting positive 0.23 volts as the cell potential under these non-standard conditions. So the original potential was 0.15 volts. Now we've increased the potential to 0.23 volts. Any questions about number 3? We're good? We're either good or we didn't do it. We're good? All right. Question 4, you're calculating Kc, the equilibrium constant for these reactions. The reactions may or may not be spontaneous, the way they're written here. If they're spontaneous, then E naught would be positive, and you'd expect to get a big Kc value. If they're non-spontaneous, E naught would be negative, and you'd expect to get a very small Kc value. I noticed there's a typo in question 4a. Did anybody notice that also? It says chromium 3+ on both sides of the reaction. So since the MnO2 is getting reduced, the chromium had to be oxidized. So the most likely thing there was that should have been chromium 2+ instead of chromium 3+ as a reactant. Okay, so you might want to change that. So the first thing I did was went to my chart. I can find the MnO2. There's the MnO2 becoming Mn2+, which is what's happening in this reaction. And its reduction potential is 1.22 volts. Then I want the chromium 2 becoming chromium 3, which is down below. Chromium 2 becomes chromium 3 is positive 0.50 volts. So putting that together, the standard cell potential is 1.72 volts. Because it's a positive voltage, this reaction is spontaneous. We can calculate Kc. We take the Nernst equation. If you look back at the Nernst equation, when you're at equilibrium, E cell becomes 0. And when you're at equilibrium, Q becomes Kc. So if E cell is 0 and Q is now Kc because we're at equilibrium, you can rearrange this and it would say E naught is equal to positive RT over NF times the natural log of Kc. We're good with that? That was used on your web assignment. So there's my equation. E naught is RT over NF natural log of Kc. And I just plug the information in. E naught is 1.72 volts. You can see from the 2½ reactions that N here is also a 2. And you put in the temperature R and F, and you end up getting that the natural log of K is 134. So Kc is going to equal E, the base of the natural logarithm, to the power of 134. That's going to be a very big Kc. It's possible on a test that you might get a number which is too big for the calculator to display, unless you have a TI-89 or something like that, graphing calculator, maybe the Casio calculators, I'm not sure. The TI-83s and TI-84s, the largest number they can display is 10 to the positive 99. If it were 10 to the power of 125 or something, this calculator would give you an error message. If that happens, then you would just leave your answer in this form, e to the power of 134, e to the power of 255 or something like that. So try to evaluate it on a test. If you can't, if the calculator says error message, then just leave it as e to the power of 255 or something like that. Okay. So let's do the last couple of these together. If you've not done it, do it with me here. If you've done it, just follow with me with the reasoning. So I'm going to need E naught, the standard cell potential. So I can see in the reaction that Fe3 plus is becoming Fe2 plus. So I'm going to find that reaction on my chart. Fe3 plus becomes Fe2 plus is right here. Can we check something? Can we review something? If Fe3 plus is reacting, that is the reactant here, Fe3 plus. Do you remember what we said would react with Fe3 plus on this chart? What's the rule that we established? You can see it down here.
Below and to the right.
So if it's on the left, like Fe3 plus, yes, Trevor, it'll react with anything on the right and below it, right? And when we say it will react, we mean it would be a spontaneous reaction with something like that. If it's on the right and above it, it would not react. It would be a non-spontaneous reaction. It would have a very, very small Kc value, right? So what's this guy reacting with? Br minus. So just looking at the chart, Fe3 plus is here. Br minus is where? Oh, it's above it and to the right. So what do I know immediately? This reaction is non-spontaneous, right? It's going to have a very small Kc value. It's going to have a negative cell potential, right? I can just tell that immediately from the chart. But let's get the numbers. Bromide to bromine would be negative 1.09 volts. So putting those together, the E naught would be, for the Fe3 to Fe2, that's a reduction potential. That's going to be positive 0.77 volts. Bromide to bromine, that's the oxidation potential. That's negative 1.09 volts. You had to reverse the equation, so you changed the sign of the potential. So 0.77 and negative 1.09 gives me negative 0.32 volts. And that's all I need to see to say that this is a non-spontaneous reaction. And that means it is not product favored, it is reactant favored, right? The reverse reaction would be spontaneous. The reverse reaction would have a large Kc. So let's go ahead and calculate Kc. I've written the equation in the last question, so I'm not going to rewrite it every time. I'll just plug the numbers in. Negative 0.32 volts, that's my E naught, is R T. What's N going to be for this reaction? We keep seeing 2, don't we? I hope you don't get the impression it's always 2. It's not, but in all these examples we're seeing so far, N is a 2. For bromide to bromine, there are 2 electrons. For Fe3 to Fe2, there's 1 electron. So you put that together, it's going to be N is 2 is the number of electrons being transferred, times the Faraday, times the natural log of K. Grab your calculator and isolate the natural log of K. What will that equal using those numbers? So negative 0.32 times 2 times 96,500 divided by R divided by T. I get negative 24.9. I usually keep an extra sig fig at least, negative 24.9 at this point, and I'll round it off to 2 sig figs at the end. So therefore, Kc is e to the power of negative 24.9, which is going to be a very small number. 1.5 times 10 to the minus 11, which makes sense. The Kc is so small because we said it was a non-spontaneous reaction. It had a negative cell potential. All right, anybody want me to do the last one there? Yes, no? Or are we good with that? All right, so we'll leave it there. Can you turn to the next worksheet, and just as a quick review and warm up, can you do questions 1 to 6? Do not try number 7. Okay. When I created this PDF document, there was some issue with the fonts, so I don't know what these dots up here are doing there. There was something about the font that it didn't like. So identify in this reaction the oxidizing and reducing agents. And then questions 2 to 6. So this is review. Hopefully you are looking at oxidation states, oxidation numbers as you do this. Do you notice hydrogen is not changing? +1 on the left, +1 on the right, so you can ignore hydrogens. Oxygen is not changing. It's -2 on the left, it's -2 on the right. So we can ignore hydrogens and oxygens in this equation. The lead is changing and the manganese is changing. So that's what we're going to focus on. The manganese starts off at +7 in the permanganate ion. It finishes at +2. So I can tell right there permanganate is getting reduced, isn't it? It's gaining electrons. So since this is getting reduced, it is the oxidizing agent. It's causing something else to be oxidized. Looking at the lead starts off at oxidation state 0 and finishes at +2. Lead is losing electrons. Lead is being oxidized. So the lead is oxidized. If the lead is oxidized, it is the reducing agent. Okay, so permanganate was the oxidizing agent and lead is the reducing agent. Which of the following is the best oxidizing agent? So you should say to yourself, the best oxidizing agent. Well, they get reduced, oxidizing agents. So I want the one that is most likely to be reduced, most easily reduced. That would be the best oxidizing agent. if it's most easily reduced, it would have the highest reduction potential. So I glance at my chart. Things that get reduced must be on the left side of the chart, right? In fact, it even says at the top, those are oxidizing agents. So if it's not on the left side of the chart, it's not going to be an oxidizing agent. We want the one that's the best oxidizing agent, so that's going to be near the top where it has the highest reduction potentials. So looking at these choices, gold might be tempting, but the gold is the neutral gold. It's on the wrong side of the chart, isn't it? So the best answer here is silver, Ag plus. Yes, silver has a reduction potential of 0.8 volts. None of the others have reduction potentials bigger than that. The best reducing agent. Well, a reducing agent gets oxidized. So I'm looking for the one that's most easily oxidized. So it has to have the biggest oxidation potential. Things that get oxidized are not on the left side of the chart, they're on the right side of the chart because we're reading them backwards. They're being oxidized. So I have to have something on the right-hand side, and the biggest oxidation potential would be near the bottom, wouldn't it? Because these potentials change signs when we get oxidation potentials. So something on the right and near the bottom is what I'm looking for, or on the right and lowest down. So which of those is on the right? And zinc is looking pretty good. In fact, I think that's the answer, isn't it? Zinc is the answer. Lithium is below zinc. Lithium's at the very bottom of the chart. But this is lithium positive. It's Li positive, not just Li. It's the wrong form of lithium, right? Which substance is able to reduce Fe3 plus to Fe2 plus? Well, we looked at that equation earlier. Fe3 plus is here to become Fe2 plus, so that's the reaction. Things that would react with Fe3 plus would be below it and on the right. So I'm looking for something on the right-hand side and below that reaction. The reason they're able to reduce Fe3 plus is because the cell potential would be positive if we have something below and to the right. So of these choices, lead looks good. In fact, that's the only one that works there, isn't it? Lead. Which of the following would be able to oxidize bromide to bromine? So we find bromide, there it is, to become bromine over here. So I want bromide to react. It's going to react with something above it and to the left, right? Bromide's on the right, so it reacts with things above and to the left. So of these choices, the bromide would react with gold 3 plus, right? Number 6, we discussed in class together. Metals dissolve in hydrochloric acid, and they produce hydrogen gas. The reason they do that is because the hydrochloric acid contains hydrogen ions, which get reduced to make hydrogen gas, and those ions will react with anything below and to the right. So there's a whole bunch of metals that will dissolve in hydrochloric acid like that. Zinc and magnesium metal are two of the common ones, but there are metals that are not below and to the right. There are metals that are above and to the right. So which ones would not react? They would be copper metal, I think, is the first one. Oops. Copper metal. Another one that would not react would be silver metal. Another one that would not react would be gold metal. I think that's the only choices there, right? There are some metal ions above and to the right, but the ions are not the metal, right? They're not the neutral metal. So those are the three choices. Mercury. Did I see Mercury? Where do you see Mercury? Mercury is not on my chart. Do you have are you looking at a different chart? I don't even see Mercury on my chart. If you have, like, for example, the chart on the web assignment, maybe Mercury would be there, but I don't see it on my chart. Okay. All right, folks, I'm going to pause the recording here. All right, so we are looking at the data results from your Breathalyzer labs. You've got your data sheet in front of you. Go down to your data table. I'm using Carlin and Miranda's data here. Just trial 1 is what I've entered. So the first thing, if you haven't already done so, calculate your volume of sodium thiosulfate that you used in that trial. So for these guys, 19.1 minus 0.8, they used 18.3 milliliters of the sodium thiosulfate. Now remember, the sodium thiosulfate's concentration, the stuff that was in your burette, was 0.010 molar. Okay. We also have, look back up at these reactions, the sodium thiosulfate, the thiosulfate ion, was reacting with that reddish brown iodine that was in our flask. And this is the reaction to 2 moles to 1 mole ratio. We're going to use that as a unit multiplier. But then look at the reaction right above that. Where did the iodine come from in the flask? Where did the reddish brown iodine come from? Well, it was a product, right? The iodine was a product when we added the 4 mils of Ki. So the iodide ions in the Ki reacted with dichromate that was in our flask, and 1 mole of the dichromate ends up creating 3 moles of iodine. So we need that ratio. 1 mole of dichromate makes 3 moles of iodine. And 1 mole of iodine reacts with 2 moles of thiosulfate. We need that ratio also. Okay, so let's go down below. It says to use your final trial. I'm going to just use trial 2 for this. So let's calculate the dichromate concentration in trial 2. So what would I start with in my string of unit multipliers?
Volume?
The volume of the sodium thiosulfate, yeah. So we have 18.3 milliliters of the sodium thiosulfate, the Na2S2O3. This is a redox titration that we're doing here, right? So this is perfectly possible on your electrochemistry test to give you a redox titration question, right? So 18.3 mils of sodium thiosulfate. What am I going to do with that? Convert to mole. Well, we will, but before we do that, why don't we convert it to milliliters? Or do you want to use to liters, or do you want to use millimoles? Want to use millimoles? I like millimoles. So let's convert it to millimoles. So we'll get rid of the milliliters and convert to millimoles of the, now technically it would be sodium thiosulfate, but the equation doesn't have sodium thiosulfate, it has thiosulfate. So let's get rid of the millimoles of sodium thiosulfate and switch that to millimoles of thiosulfate. Please ask if something doesn't make sense. What is the first unit multiplier? What is millimoles of sodium thiosulfate and milliliters? What is that? Yeah, that's the concentration, isn't it? We usually think of it as moles per liter, but it could equally well be thought of as millimoles per milliliter. So when it was 0.010 molarity was the concentration, we can go down here and say 0.010 millimoles per milliliter. And what numbers go in the next multiplier?
1 to 1, right?
Why is it 1 to 1? When you look at the formula for sodium thiosulfate, how many thiosulfates are in the formula? Just one. So 1 millimole of sodium thiosulfate has 1 millimole of thiosulfate, right? Now where am I going to look? Or what will I do next? Somebody, what will I do next? We've got millimoles of sodium thiosulfate right now. We're trying to figure out the concentration of dichromate we're trying to get to.
Would you convert it to iodine?
Yes, we would. So we're going to convert the millimoles of thiosulfate to millimoles of iodine, I2. How do we do that? By looking at that second reaction up above, right? What numbers do I put in there? Two moles of thiosulfate for every 1 mole of iodine, right? That's the stoichiometry. So 1 mole of iodine for every 2 moles of thiosulfate. Then what?
Convert to moles of dichromate?
Yeah, convert the millimoles of iodine to millimoles of the dichromate. That was the orange colored compound, right? The dichromate. I need to look at the other balanced equation for this, don't I? Hansu, what number goes on top? What number goes on the bottom? 1 and 3. You're right. 1 mole of dichromate for every 3 moles of iodine, looking up at the other balanced equation, right? Now we're almost there. We have millimoles of dichromate, but we're trying to find its concentration. So what do I need to do as my last step? Divide by the volume. Volume of what? Since this is millimoles of dichromate, we're going to divide by the volume of the potassium dichromate. Now you could say maybe we should switch to potassium dichromate, but let's skip that step. We're going to divide by the volume of the dichromate, right? Now, who can remember from the lab what volume of dichromate was in the flask? Do you remember doing it? You did it over and over and over again. At the very beginning of the experiment, I gave you 200 mils of potassium dichromate, and we added 3 mils of alcohol to that. But that's not what you titrated, is it? You didn't titrate the 203 mil sample. You were pulling out how much of it? 10 mil samples into your flask, right? So that's what you were titrating, was a 10 milliliter sample. So we're going to divide this by 10 milliliters. Grab your calculator and get the concentration of dichromate. There were only 2 sig figs in the concentration of sodium thiosulfate, so we'll just keep 2 sig figs in this concentration. 0.0031 is what I get using the girls' data here. If you recall, it says it on the data sheet, the starting concentration was 0.0036. So this is reasonable, isn't it? It had reacted with the alcohol and had fallen to 0.0031 after 6 minutes. Okay. So am I going to do this over and over and over again to get these answers down below? I suppose I could, and if this was 1990, yes, I would. But this is not 1990. This is 2021. We can use either our graphing calculator or we can use a spreadsheet. When I showed you the graph earlier, I had used Microsoft Excel to do it in just minutes. I had done all the calculations. Can we do this on our calculators pretty quickly? I think we can. So go to Stat and Edit on your calculator and clear up some lists. I'm going to clear up all of my lists here. Oops. Press Clear, Enter. Make sure your cursor is up on top of the L3 or L4 symbol. Clear and Enter. Just clear a bunch of lists. In list 1, let's put our times. I'm looking at the screen here. It's a little blurry. Hopefully you can see that a bit clearer. So in list 1, let's put our times. Now, we said we would put the times in seconds, right? So I'm going to take this data 6 times. My first time was 6 minutes and 1 second. So that would be 6 times 6. How do I just do this? It's 6 times 60 plus 1. Hey, there I go. The next one was 12 minutes and 2 seconds. So 12 times 60 plus 2. All right, so fill in your times in the first list. I'm using the data from the girls here. You're using your own data. If you already converted them to seconds, then just copy in the seconds. And then 30 times 60. 36 times 60 plus 1. 42 times 60. And 48 times 60. In your second list, the simplest thing, if you're able to do some mental math, would be to put the volume used for each trial. If you're not able to do the mental math, then I suppose you could put the initial volumes in one list and the final volumes in the next list, and then we can subtract them to get the volumes. But I'll do some mental math. So now I left out one data point. I left out the 0 data point. Can I go back and enter it? If I put my cursor on the first data point and go second function insert, hey, yes, it does let me. I can insert right above the delete button. It says INS insert. So the first point there, whoops, the first point doesn't have a volume, so I'll leave that. My second point though, whoops, I'll just put a 0 there. I have to put something. So I'll put a 0 there. It doesn't really matter. 361 seconds, I've already know that's 18.3 milliliters. Then 15.3, these girls already calculated these numbers. 13, 10.8, 9. So you're putting your own numbers. You're not just copying these. 7.5, 6.3, and 5.2. I may have a problem on the graphing calculator with that first point. That may be a problem. On the spreadsheet, I don't have this problem on Microsoft Excel, but on the calculator, I might have to delete that first point. But let's just keep going. Anybody not here yet? At home, anybody need more time? Everybody's got these volumes entered? Okay. Then list 3, I am going to delete. Actually, no. I'll leave it for now. Put your cursor on top of the L3 symbol. Now look at what we did with our unit multipliers. What did we do with the volume? We times it by 0.01. Then what did we do? Well, we can skip the next one. It's just ones. We divided by 2, right? And then we divided by 3. And then we divided by 10. Didn't we? So let's just say L3 is equal to what?
L2
L2, then what?
and divided by
Times it by 0.01, then divided by 2 and divided by 3, or just divided by 6 if you like, and divide by 10, right? And press enter. Okay, I'm going to ignore the first one there. Actually, no, it doesn't really matter. So 0.0031 is the first one there. Actually, I'm going to go back to my first point there on my screen. My first one, what should the concentration there be? What should that first concentration be? 0036. So now I'm going to go back and change that first data point, 0.0036. There we go. All right, so now list 1 is my time. List 3 is my concentration. What 3 graphs are we going to make? Now comes the kinetics. Do you remember your kinetics? What 3 graphs are we going to make? To test if it's 0 order, we're going to graph the concentrations and the times. So right now we can already go make the first graph. What's the second graph to see if it's first order? We want
Natural logarithm.
Yeah, the natural log of the concentrations versus the time. So go to list 4 and put your cursor up on top of the L4 symbol. We want the natural log of our concentrations. So we're going to take the natural log of list 3, right? The concentrations, and press enter. Hey, look, natural log of negative numbers less than 1. They're all negative answers. And what's the second order graph? The reciprocal of concentrations. Yeah, so put your cursor up on L5, and this time I want the reciprocal of the concentrations. So I'm going to type list 5 is equal to what? What is 1 divided by list 3?
Yeah.
And I get big numbers, 1 divided by small numbers. All right, so we can make our graphs. Are you ready? Anybody not with me at this point? So let's make our first scatter plot. Second function, stat plot, right above the y equals. We'll use plot 1 to do our 0 order graph. We'll use plot 2 to do our first order graph. We'll use plot 3 to do our second order graph. So for plot 1, make sure plots 2 and 3 are turned off right now. I'll go to plot 1, turn it on, make sure it says on. The first type is my scatter plot. What do I want my X list to be?
1.
But what has to go there? The time, and times are in list 1, right? What has to go on the Y axis for this graph? Concentrations, which are where for us? Yours might be different, but for mine, it's list 3, right? So second function, L3. So I'm ready to go. How do I see the graph? What do I press on the calculator to see the graph?
Zoom in.
I go zoom, the zoom button, yes. And then option number 9, zoom stat. And I get that graph. So you could sketch on the back of your handout, sketch on the back. This is a test, is it 0 order? And you could sketch the graph of, make sure you label the axes, concentration of dichromate versus time. And what's the conclusion that that gives you?
Is it supposed to be curved or straight?
So we're looking for the graph that's linear, right? So what's your gut telling you? Is it 0 order?
No.
That's a pretty smooth curve, isn't it? So I'm going to guess that it's not 0 order, and I'm going to sketch that on my back of my handout. So in your sketch, make sure you label the axes. Concentration of dichromate is your y-axis, and time is your x-axis, and your conclusion when you've sketched is that this is not 0 order.
I have a question.
Yeah.
For our first data point, it was kind of bad since it was our first one.
So the first, do you mean your first titration
Yeah.
data point, or
Yeah.
the first point 0.0036?
Like titration.
Yeah, so if you know for sure one of your data points had an error, or you went too far or something, you could delete that point if you'd like from the data set. But make sure you delete the time also, right? You can't just delete the concentration. You have to go back and delete the time also, and you have to delete from all the columns, right? All right, so let's make our second graph. So I'm going to go to stat plot again. Turn the first plot off. So select it and go put your cursor on the off and turn it off. Then go up to plot number 2 and press enter. Okay, so now plot 2 is selected. Turn plot 2 on. So plot 1 is still there, but now we're going to make plot 2. My X list should still be time, right? So I want L1 to be the X list. My concentrations were in list 3, so the natural log of concentrations were in list 4. So I'll put L4 as my Y list. This is the natural log of dichromate concentration versus time. And I want to see the graph. I press zoom and option 9, zoom stat. That looks pretty nice, doesn't it? That looks pretty linear to me. So sketch that. Okay. Strong suspicion is that the dichromate is first order based on this. Your y-axis here should say natural log of concentration of dichromate, and your x-axis should say time, right? Anybody else get a graph that looks pretty much like this graph's perfectly linear? Anybody else get something like that?
No,
Yeah.
perfect. Doesn't look like that.
In a moment, we'll put the line of best fit through and you can visually see it. So now let's make the third graph. So go back to stat plot. Turn plot number 2 off. And go up to plot number 3 and select it. And turn plot number 3 on. This is my second order test when I want the reciprocal of concentrations versus time. So my X list is still list 1. My concentrations were in list 3. My natural logs were in list 4. So my reciprocals were in list 5. So I want L1 and L5. And now I want to see the graph. I press zoom. Option number 9. And that does not look linear to me. That looks curved, right? And rising like it should, but it's a curved graph. So the fact that the second graph, natural log versus time, was linear and the other two graphs are curved is telling us that it was a first order in dichromate. Can we calculate the rate constant for the reaction? It's a bit of a trick question. Can we find the rate constant for this reaction?
They don't have it.
This is a while since we've done kinetics, but remember that the actual rate law said K, the rate constant, dichromate to the power of X. We now know that X is a 1, it's first order. But there was also the alcohol and there was the acid, right, in the rate law. What did we do in this experiment? We used those concentrations to be very, very, very large so that they were constant. So if they were constant, then they could be combined with the rate constant to make the pseudo rate constant, K pseudo. So can we actually find K? No. But can we find K pseudo? Yes. So we can find the pseudo rate constant, but we can't actually go find K. So let's go find the pseudo rate constant. How do I get the pseudo rate constant? We need to look at the slope of the linear graph, right? So we need the slope of the linear graph. So go turn this plot off again. Plot 3, turn it off. And go back to your linear graph, which was plot 2. Turn it on. And zoom number 9, just so we get it back on our screen. All right, so there's that linear graph. I need its slope. What are we going to do? What's it called? Linear regression, right? To find the equation of the line that goes through the graph, linear regression. How do we do linear regression? We press the stat button. Then where do I go? We go to the calc menu to the right, and we choose option number 4, linreg. There is also option number 8, and I honestly don't know. One is ax plus b, the other is a plus bx. I have no idea why you would want them written in 2 different ways like that, but I just use option 4. And on the older calculators, your screen will just say linreg at the top. You have to type in L1 comma L4, right? L1 comma L4. On the newer calculators where you have this, you'll type in that the X list is L1, the Y list is L4. For the people with the older calculators, you typed in L1 comma L4. Then if you want to see the line on your graph, you would type another comma. For the rest of us, we just go to store regression equation. And then we go to vars, variables. We go to y variables. We choose functions. And you could pick any one of them. We'll pick y1. So for the people with the older calculators, your screen at the top would say linreg L1 comma L4 comma Y1. We went to vars, V-A-R-S, then we went to Y variables, we chose functions, and then we picked Y1. So now we can press calculate or press enter on the old calculators. And there's my slope, negative 4.9 times 10 to the negative 4. which means the pseudo rate constant is positive 4.9 times 10 to the negative 4. That's the slope of the line, negative k. Just to verify, press the graph button. And that line goes right through the data. All right. The more linear this line is, the better your titrating was, right? So if you have some points that are a little bit above or below the line, that's okay if it still looks pretty much linear. But the more points you have above or below the line, then the sketchier you were at titrating. You might have gone past an equivalence point, or you misread the volume or something. Okay. So I hope you appreciate the complexity of that experiment. We were able to determine that the dichromate is first order. We were able to determine the pseudo rate constant, and we did that all using redox titrations, right? The connection to electrochemistry. And we were studying a breathalyzer reaction, which is itself a redox reaction. So we were doing a lot of stuff in that lab. All right, it is 3:27. Folks, in your handout, if you look at your worksheets again, the electrochemistry worksheets, scroll to the last or go to the last page of your handout. There is a 2-page assignment there called corrosion and its prevention. There are some QR codes there. Everybody sees that? So there's 2 little videos to watch from, I think they're both on YouTube, that talk about corrosion, rusting, and some simple techniques to prevent it. As you watch the videos, the answers to these questions are found there. Okay, so I want you to finish this by Wednesday. Okay, so between now and Wednesday, finish off that worksheet, watch the 2 little videos. It took a little bit more time than I wanted at the beginning, so I didn't get to discuss the web assignment. I think it's due tonight. I think I extended it to be due tonight. If anybody has specific questions on the web assignment, then hold on to them till tomorrow at the start of class. If I have to, I'll extend the due date for you till tomorrow, and we'll discuss the questions from there. Okay, we're going to wrap up electrochemistry this week, and there will likely be a test probably on the weekend, maybe on Monday or something like that. Okay. All right, folks at home, enjoy your day. Take care.
Excuse me, Mr. Patnode.
Yes, Ivan.
Could you please give me one more try at my electrochemistry web assignment?
Yes, I'm going to look at it right now, and I'll give anybody an extra try who needs it. Okay.
Okay, thanks.
Goodbye.
Oh, and one more thing, Mr. Patnode.